Before we move on, the idea of minimizing loss functions is typically not done with some nice visual software. Usually we're using something like Python or some programming language to execute it. As we notice, there are a lot of redundant computations that can easily be allocated to technology. So the first thing that I'm going to do in this program is just import some packages. I don't actually think that we need math, but we'll use NumPy and Matplotlib. NumPy to work with arrays, Matplotlib to work with graphing. So the first thing I'm going to do here is I am going to define the loss function, the SSR, and the way I'm going to do that is it will accept an array of x's, y's, a slope, and an intercept. All it will do is it will return the sum of squared residuals. So it's y minus the quantity mx plus b, which is y minus mx minus b squared. So it'll sum all of those together that it gets here. So x and y are arrays, meaning it knows to just sum the column of differences squared that we get here. Excuse me. The next thing that we'll do is we'll define the derivative function. And keep in mind that the derivative is typically going to be done with autodiff, backpropagation. But because this function is nice enough, we'll just go ahead and take the derivative, which is, remember, it's 2 times this quantity to the first power times the derivative of the inside, which is negative x, because we're taking the derivative with respect to m. And here's just our data. So here is the number of hours of sleep, GPA, number of hours of sleep, next GPA, and so on. Now I want to only optimize with respect to the slope. I want to fix the intercept equal to 0 here. That way I'm only dealing with a univariate problem. Okay, so the next thing we want to do is define our step size, and I am going to define this to maybe 5 decimal places. I want to get a pretty exact estimate of that slope here. Down here what I have is just, I'm going to keep track of the slopes. So the m's, that's what I'm referring to as the m's vector, and the SSR's vector, list actually. And what we will do is we will take the current m, which is the initial one, and we'll append it to the m's list, and then the SSRs will append the first SSR corresponding to that very first slope. So that's just going to give us essentially the value of, I think it was m equals 1 with an SSR. I want to say it was somewhere around, 54.1. And then what we're going to do is I'm going to create this little parameter here that this is essentially going to be our tolerance. Right now, because we're starting off, I'm going to set that SSR diff really big, really large. And all this will end up being is the difference between the SSR at the previous iteration, so like this SSR minus this one, and that will give me that difference of approximately 32 units. And so once that difference starts getting below 0.00001, then the algorithm will terminate and it will output the slope that we get. Now I'm setting this to be really large right now because I don't have any differences. And I'm going to keep track of the number of iterations. So while SSR diff is bigger than 0.01, so I'm going to set that to be my tolerance. Oh, I'm sorry, this was my H value. My H value we had set to 0.001. I want this set so that basically the SSR diffs are really not changing anymore. The first thing I'm going to do is compute the new m. So remember, that's going to be m plus or minus h times the derivative corresponding to the current m given our data set. Again, b is 0, so it's not really doing anything here, but I just put it in there as a parameter. And the reason I'm doing a minus here is because if the derivative is positive, then we want to decrease the value of m. If the value of m is of the derivative is negative, well, then we want to increase the value of m, because, you know, this from here to here, at this point we had a positive slope of around 197, so we wanted to move back in the other direction, so that we're decreasing the sum of squared residuals. And so if our slope here were to be negative, well, then we would want to move to the right. So a negative slope times a negative h will give us a positive change in m. So that just handles that, so we don't have to worry about the sign being plus or minus. Okay, so then I'm going to add that slope to my list because I want to take a look at a graph later on that you'll see in a moment. I'm also going to add the SSR related to this new m that we just calculated. I'm going to append that to the SSR's vector. And now I'm going to compute the new SSR difference. So that's just going to be the SSR at the current iteration minus the SSR at the previous iteration. So essentially, if we go back to this, it'll be the SSR minus the SSR. And I'm going to take the absolute value of that because I don't really care if it's positive or negative. It really should be positive, right? Because I want to make sure I'm always decreasing the SSR. So the previous, or the current, sorry, this should always be negative. But anyway, so that I could set that to be greater than 0.00001, I'm going to take the absolute value of it. And then I'm going to increase the iteration. I'll also add in here, if iteration exceeds 1,000, then we're going to just break. We're just going to terminate out of the while loop, because that just essentially means that we've gone too far. And I will just also make a print statement, error, max iterations exceeded. So this is just in the event that our value isn't converging. We can tell after 1,000 iterations. Now, after that loop, I'm just going to print the value of m that was found, and that's just the last value of m before the while loop terminated, assuming there wasn't an error. Finally, we will go ahead and plot the m's versus the SSRs. We're going to use little circles to indicate where the SSRs are, and then we're going to connect the dots. And you'll see why this is interesting when we actually change this step size to something a little more unconventional. Okay, so let's run this. Okay, so notice no error. It found the slope to be 0.4549. And if we come back here, our 0.4547 was the correct value, but because there's a certain level of precision that we set before this thing terminated, we could always make that bigger, and I run it again, 0.4547. If I make it even bigger, 0.4547, which you can see we're getting very, very close. We have a very low tolerance. It just depends on how many digits we need to round to in our machine learning algorithm. So the other thing that I extract here is I will extract the plot, okay? And I will go ahead and run this. And this will give me a plot showing us the value of the slope. I don't have this labeled, but we have the slope along the horizontal axis. There we go, got added those labels in. So we have m along the horizontal axis, we have SSR of m. We started here, and you can see that the path is followed from right to left until over here we converge to the minimum value. You see a lot of dots there, a lot of points, because we're getting very, very close. If we go to the Variable Explorer, we could actually see our whole list of SSRs, and you can see that the algorithm does end up terminating because you can see that the SSRs are starting to look pretty much the same. In other words, there is very, very little change to the tolerance that we set. You can also see these slopes started at 1.8026. This should all be familiar from what we did in the previous example, and you can see we are converging to that correct slope. Now, the reason I wanted to have those dots connected is because I'm going to show you something interesting. Depending on what h is, if h is too big, like here, this will actually turn out to be too big. And the consequence is we're going to get a runtime issue. And the runtime issue that's going to happen here is actually because the values start to explode. But let me go ahead and show you. Okay, so you see we do get a runtime error here, and something wacky is happening. You actually see the value of m, and notice the scale on these axes. This is not -2 to 6. This is -2 times 10 to the 152nd to 6 times 10 to the 152nd. And you can see that we're sort of jumping everywhere. We're jumping all around. And this zigzagging that we see, we don't really see all of the details here, but you can see it's terminated after 369 iterations. And the reason for that is, I want you to notice, look what's happening to the SSRs. They're actually getting bigger and much, much bigger. And that has to do with the fact that if we look at the SSR prime, the original SSR prime that we had, 197.4, that was our initial one. We multiplied that by a learning rate of 0.001, which give us 0.197. But if we only multiply it by 0.01, that gives us 1.9. So effectively what we're doing is we are going to decrease our m by 1.97. And you can actually see that here, the decrease went by 1.97. Then we used that slope, calculated our SSR, figured out what our change is, and then it jumped to 4, and then -9, and then +26, and then -66, and then 176. So essentially what it's doing is, you follow my cursor, the slopes are wildly jumping back and forth until we get to such a large magnitude that eventually the computer says, I'm done, I'm overloaded, and I'm getting an overflow. So this is a perfect example of where instead of getting convergence, we get divergence, and those errors get infinitely big. So actually what happened is we started down here, we got these oscillations until we started to get these wild oscillations, and the computer did not like it anymore. So in our next video on this, we'll take a look at, well, how do we do this with the value of b as well? And the only difference is we're going to need the gradient vector, which will still contain a derivative with respect to m, but will also have a derivative with respect to b.